looks good.
I'm not sure if I should have a microphone
oh,
from the speaker.
He was using this podium mic. Would you like to wear this?
No problem.
Okay, all right.
I think that should be fine. Okay, welcome. Thank you, Ariel. Thank you, Ernst. Thank you, Andrea, not here, for organizing this. It's really good to be here. Being a speaker has the additional advantage of not wearing a mask, so for 30 minutes I'm free here. I have to quickly speakers the attendees of my slide. Okay. So I would like to talk today about new results from nanoscale friction from our laboratory. I will actually extend the abstract a little bit because after 2 years I would like to really talk about 3 works by 3 PhD students, Bartosz, Günther, and Roland. And one of the essential parts here is in collaboration with Michael Mosler and his group, in particular with Leo Meyerhofer and Takuya Kuwahara, who have done simulations for a phenomenon that we have never understood, but we have measured consistently over the last 13 years or so. And I'm putting here artwork, a brush of a good friend of ours who specializes in polishing crystals in a way such that you're never sure if they are solid or if they're liquid. And that is actually a phenomenon that we observed for lubricants, which are confined between the egg and tip and the surface. And so we're really never sure if they're liquid or solid. So topic number 1 is actually about graphene on steel, real steel. So we polish a steel surface, we put graphene flakes on the steel surface, and we were wondering how this will change the lubrication capabilities of hexadecane as a model alkane lubricant. And what turns out is that graphene helps the lubricant to sort of form a layer that can support load. So what you can see here is images. On the left is a topography image, on the right is a friction image. The steel has a certain remaining roughness, for sure. And what you can see is that there is actually graphene on the right side of the frame and no graphene on the left. And we see that only in friction. In topography, it's impossible to see this one layer graphene. But in friction, you see that the friction is actually greatly reduced. These are measurements in hexadecane with a sharp end tip. So we have a reduction of a factor of 3 on the graphene. And what we have done then is we have taken so-called force distance curves. So we approach in hexadecane the eighth end tip to the surface. We plot here the tip sample distance, so we have subtracted the bending of the cantilever. And what you see on the upper graph is the force versus tip sample distance. The blue curve is above steel. So what you can see is there's no force, no force, no force, no force. Then there's a little hiccup just before the steel, and then there's the hard wall of the steel. Now, if you do the same above graphene in hexadecane, that's the black curve, you actually see that there's a layering. You can observe layering of the hexadecane in the confinement of the tip. You see 4 layers, 3 layers, 2 layers, 1 layer, and we could not penetrate the last layer of hexadecane on graphene without breaking the whole system. And you can also see that we have a distribution of many, many curves and systems of the layering range. And you can see here that the layering range extends up to 4 nanometers sometimes on top of graphene, but rarely more than 1 nanometer on steel. So somehow the graphene on the steel helps sort of building ordered layers of the hexadecane which can carry load, and that probably is the reason that the friction is reduced. And then if you actually look into high-resolution images, friction force microscopy, you see that there's these stripes, and within the stripes you see little atomic structure, and I have sort of suggested here in white rings the structure of the alkane lying in these lamellae. And this has been confirmed before in many experiments on flat surfaces like copper or so by STM, also in hexadecane. And what happens is essentially alkanes fit surprisingly well to graphene structurally. So they like to order form Orders layers with a little superstructure here, and we get regular stick slip on these lamellae on the alkane layers, and then we get this low friction, while we get this very irregular and large stick slip on the steel surfaces. So this is essentially one result from Günther's thesis that I never talked about before, and I just want to show it here. Topic number 2, which is maybe the core of today's talk. So we have been working on a sample which is quite spectacular for a long time now, silicon carbide as a crystal, and then one layer graphene on top. So the silicon carbide is sort of finished with a carbon-rich layer that has graphitic structure, and then there's the van der Waals gap, and then there's the graphene. And this is essentially what it looks like in a model. So you have the silicon carbide, then you have the graphitic top layer of the silicon carbide, and then you have the gap, and then you have this crumbled graphene on top. And we got interested in friction on this layer. And there's a paper by Tobin Philliter a long time ago where he shows like 2 layers have different friction than 1 layer, but that's not what I'm interested in here. What we found always is that at certain threshold load, suddenly the friction goes up. And that was different loads, but it's always there. And what Tobin did was he went to non-contact mode, and he could image, on the left image, the perfect structure of the graphene. So nothing is really flat graphene, and there's a monatomic step here. And then he would take, with the same tips, atomic stick slip images at high load, at the very high load that is beyond the threshold. And then he would take the same tip again to do non-contact imaging. Nothing changed. This is not wear. So we have a non-destructive transition to a high friction regime. And we were scratching our heads all the time what this high friction regime is. And then there was a paper by Elisa Rido's group, and also Area was involved. What they said is that if you press with an AFM tip, the pressure you apply to the graphitic system here is high enough to induce by pressure a SP2 to SP3 transition. So essentially, you make diamond under the tip for a short time. And, but you need the silicon carbide hard surface to do that. And they also found in the DFT calculation, this is on the lower right panel here, they found that there's actually a minimum. So if you press this together, you will drive the system over a barrier into this diamond state where it will rest. Yeah? But note that here, the yellow stuff, which is the confining silicon carbide, is not saturated with any bonds, which will become very important. What we thought was, this is probably our friction. We are sliding with the tip over the surface, we increase the load, and suddenly we need a lot of energy to produce diamond, which we will never get back, because we are sliding already, we moved on before we get the diamond to pop back into SP2. And this was our idea, and we tried to simulate this, and it turned out it doesn't work. Let me first show you a few new results. We have done this again and again, and we find if you take a fresh tip from the box, super sharp oxidized tip, and you do this experiment, the transition here is actually around, what, 80 nanonewton. If you do it a second time, the same experiment, the transition is already at 90 nanonewton. So the more often you do the experiment, the higher the transition. So obviously we are flattening our tip and the pressure is going down. So in the upper panels, we took out the tip after doing 2 experiments and went to TEM and looked at the tip. And I don't know how well this can be seen here, but this is a silicon tip, and you can see the silicon atomic rows up to 2 3/4 of a nanometers before the end of the tip, and then you have the amorphous oxide. So the experiment is actually done with silicon oxide, amorphous silicon oxide. And on the lower panel, you just see a tip. The green dots are actually the very first experiment. So again, 80 nanonewton for the transition. And then the black is actually the 4th. And it's a similar thing here. The longer, essentially, you do this, the higher the force at which you get the transition to this high friction regime. The high friction regime is very scattered. It's going up and down, and sometimes very high, sometimes not so high. This is very unpredictable. But when we go back, we go into this low friction linear regime again. So that is all reproducible. Okay, so the simulation runs like this. This is a tight binding simulation, and here are some technical things which I do not even really understand, except that that there's no van der Waals correction here. Sliding speed, as usual, is super high compared to our experiment, 10 to the factor of 10 to the 9 different. And let me just show you one simulation. So this is equilibrated, and then it starts sort of sliding at some point, I believe. And what you see is that there's actually a couple of things going on. The first, we do have bonds in the graphene layer. So there's actually sp2, sp3 transition, but we also have covalent bonds between the silicon oxide and the graphene surface, and there's both silicon carbon bonds and oxygen carbon bonds. And now we got interested to see how this all works. And there's one important observation. I have to walk you through this transparency here. So on the upper left, you see the shear stress as a function of time, so when we start scanning. And on the second graph, you see actually the number of bonds in 5 different trajectories. It turns out we have to do simulations with different silicon oxide configurations, because it depends very much on the details of the structure of the amorphous material, what happens. But what we can see here is that the number of carbon silicon oxide bonds is absolutely congruent with the shear stress. So our friction is determined by the covalent bond between the upper graphene layer and the silicon oxide tip, while the number of CC bonds, which is the third graph from the left, actually doesn't matter. I mean, they're there, yeah, and they are often co-localized with the covalent bond through the silicon oxide, but they do not contribute to the friction by themselves. So on the most right panel, you can see that the number of bonds where the shear stress are separated here for CC bonds and carbon silicon oxide bonds. And you can see that at 0 shear stress, we already can have some of these diamine bonds, of these diamond bonds, but friction is not going up, essentially. Friction goes up as soon as we have covalent bonds to the silicon tip. And so if you summarize this, so here you see results for 5 simulations, for 5 different configurations of the silicon oxide tip. And you can see we have a linear, more or less linear regime at low pressure, where we have something that I assign, it's a Prandtl-Thomson type thing. It's just elastic, it's purely elastic, and it's just relaxation of some elastic energy. And then we have a sudden transition, but actually in the transition regime between 7.5 and 12 gigapascal, it often jumps up and down. So we have a lot of chaotic back and forth of configurations, plastic events in the silicon oxide, and that is actually, I believe, what gives us in the tip these large scatter in the friction force values. And as I showed you already, we know that there's plastic flattening of the very sharp asperities at the end oxide. So it doesn't make sense to give too much detail on a Hertz model and the tip radius, because the tip radius that's essential for the transition is very small. I think we have small micro asperities that are being flattened. Overall, the tip radius is like 5 nanometers, but that would not give us this pressure at the relevant force.
Could you just very briefly say what you mean by pressure? I mean, it's one-dimensional, right? You come from the top, you can flow to the sides.
No, the simulation actually is not, it's periodic boundary conditions.
So it's really hydrostatic pressure.
Yeah. Okay, so we can discuss later, maybe over coffee. How many minutes do I have left?
You have, you've got 10 minutes.
Yeah, okay. So that brings me to the third unannounced topic, something else. I wanted to share a little bit with you results from Haoran Ma, who is now returned to China and under very difficult conditions, as you can imagine. He worked on metallic glasses in electrochemical solution, and we got interested in, can we switch friction on a metal by electrochemical switching, oxidation essentially. Now, originally I was very interested in doing electrochemical AFM on steel. It turns out that this is practically impossible, and the reason is the power of AFM is on the nanoscale. But electrochemistry on steel happens at grain boundaries and at inclusions. But these inclusions are never nanoscale. They just explode. It's a little bit like if you would take a profilometer and go to a volcano and try to image something. It's possible, but it's useless because you don't actually image the relevant things. So then I said, oh, if that's not possible, let's look for a metal without any dislocations, grain boundaries, and anything. So that's a metallic glass. A metallic glass is theoretically perfect. Yeah, it's just without any structural defects, or if you wish, it consists of structural defects. That depends on your view. So happily, University of Basel is still doing high-quality metallic glass films, and they gave us samples. So, as I said, so we have these little volcanoes and that doesn't work, and so we hope that there will be some smiley on electrochemical AFM here. And actually, just to tell you, we have done a lot of work on these perfect electrodes. For example, on gold electrodes, you can do beautiful work on electrochemical switching. So we have an electrochemical cell, we do AFM friction experiments, we change the potential, and we see that when we oxidize the gold, friction goes up, and when we reduce the gold back, friction goes down again with a big peak when it's reorganized. So that works on a gold electrode, and we have done a lot of work on this, mostly with Florian Hausen. Now to this metallic glass. So what you see on the upper left is a current density versus potential curve. This is a so-called polarization curve. And what you can see here essentially that there's a so-called passive regime which extends to, let's say, 0.5, maybe a little higher volt in potential. And then it starts oxidizing, and then you have a transpassive regime where the whole thing starts oxidizing, and if you wish, it starts bubbling. I mean, it's not really bubbling because it's a metallic glass, but a lot of things happening. So after we polarize this, after we go to an oxidizing potential, we go back to open potential, open contact potential, and then we do friction force microscopy on the surface. And the result is in the lower left. The problem is, originally we wanted to look into the active process, but that's very difficult. If you change the potential while you're scanning, you get a mess of results. And the reason is that oxidation produces a soft layer on top of the metallic glass, which the tip is removing all the time. So we have two time dependencies. One would be the oxidation, and the other would be the removing of the oxide layer. And so what we do here is we first oxidize, stop, and then do friction force microscopy, and you can see that the friction is going down as a function of cycle number, how often we scan back and forth, and as a function of load, we see that actually sort of the friction goes up with higher oxidation potentials, and our idea is essentially is sketched on the upper right. So we have the bulk metallic glass, then we have an oxidized layer where the metallic glass itself is oxidized, but then we also have oxy-hydroxy products which actually are released, diffused to the surface, are loosely attached to the surface. We call this the outer layer. It's not our word, it's the word of this corrosion community, the inner layer and the outer layer. The inner layer is something like 1.5 nanometers. The outer layer is unknown usually because its density is low, and this outer layer we can simply move away with an AFM tip. And that's what's happening here essentially. This decrease in friction force is we need extra friction force to remove the layer, but once it's gone, we actually have a stable system. So if we image this scanned area, we have a sort of a problem because you can do two. So we scan a little frame here, little ribbon, if you wish, and then we image the whole result. If you go to extremely low load, you can actually see that the topography is depressed a little bit. This is on the left panel, upper left panel. So at very low load, you can see that you scratched away this outer layer, but you don't see anything in friction because we are imaging at zero load. And at zero load, there's zero friction and there's no friction contrast. What we can do also is after removing the outer layer, we can image at a little bit higher load. That is the second panel from top. And then you see hardly anything in topography, but you see actually a great friction contrast. So friction is lower where we had already removed the outer layer. So it's pretty delicate because you practically can never image without changing the surface. Now, what about the potential dependence? So we can, of course, measure the adhesion force, and we find that adhesion is going up if we oxidize as a potential up to 0.6, and then it's flat. And the friction force, actually, for the inner layer increases with oxidation potential, and we believe that this inner layer is probably just roughened. So when we oxidize the inner layer, we get an oxide, and the oxide simply has a higher potential, higher friction than the original metallic glass had. And the red dots in the middle frame are actually is the friction which is according to the outer layer. So when we are still removing the outer layer, and this goes through the roof when we oxidize at high potentials. So this brought us to this picture, which I sort of sketched initially, that that the inner layer is essentially a hard and solid oxidation product, while we have metal oxide diffusing to the surface and actually into the solution, and in particular in the transpassive regime, when we actually dissolve the surface essentially by oxidation, then we have a lot of this squishy, squishy outer scum layer that is just loosely on there, but gives a lot of friction initially. So be warned, if you do electrochemical anything on metallic glass, there is, of course, the oxidized surface, but there's also a lot of corrosion products just hanging at the surface, not really in the surface, on the surface, more like at the surface, I would say. Harran also got very interested. I mean, he originally wanted to start with compare NaCl, borate, and phosphate buffer, but NaCl is actually too strong a solution, so this will just kill your metallic glass. And the reason is that the metallic glass is actually not really perfect. Even this Basel samples are locally fantastic. You will always find 100 by 100 nanometers, which are absolutely homogeneous, flat, nothing there. But then every, let's say, 2 or 3 or 4 micrometers, you will find some sort of inclusion. And these points start bubbling like hell if you do sodium chloride as a solution, and that makes your solution actually brown, and AFM doesn't work anymore, and all this stuff. But borate buffer and phosphate buffer worked, and these are a little bit different in how aggressive they are. And we found that by simply immersing our metallic glass into these two buffers, we got different friction on the same metallic glass. So just immersion led to different friction coefficients, and so how's that? So Harran actually did a lot of atomic scale friction studies on these surfaces, and he found that there is stick slip. There's actually even atomic or nanometer scale stick slip, very similar to crystalline surfaces, but really hard to understand. But what we see here right away is that in this borate buffer, the sticks are larger and they jump farther on the same surface, essentially. Yeah? While on the phosphate buffer we have slips which are actually exactly at what these metallic glass people call the local cluster, which is at sort of clusters of 5 or so atoms, or maybe 8. So these are really 1 nanometer scale stick slips. So we have increasing slip length at higher loads. Now what he wanted to do is, he said, let us do Prandtl-Tomlinson model for amorphous surface. There's only one publication I know of with a model of stick slip on amorphous surfaces. So he tried to do the experimental physics approach, which means take a successful model and try to expand it towards what we need. So what he's done here is he has done this classical way of plotting force versus distance. So we have a sinusoidal force, which originates from some periodic potential, and we have these curves which correspond to a certain stiffness, local stiffness of the contact. And then you get an instability, essentially, when your force is high enough to overcome the maximum force, you will jump to the next minimum, and you will jump along the path of your stiffness, essentially. And then he has simply changed the potential. I say, well, amorphous surface means either that the potential is locally higher or lower, which is the upper panel with the blue and the red curve, or that actually the distance to the next minimum is larger or smaller than for a periodic surface, which is the lower panel, red and blue curves. And then he calculated essentially the lateral stiffness values K1 and K2, which indicate on the one hand the transition from smooth sliding to instabilities to stick slip, and K2 would be the value for the stiffness when you move from single slip to a double slip, when you just skip one minimum and just jump to the next but one, which Rob has shown actually is very important to quantify friction. And then he has simply analyzed the data we have, which is taken on the amorphous surface, and he has calculated all these little slopes, and he has calculated the slip heights, the maximum forces for slip, and done all the distributions. And here you see essentially 4 graphs, which essentially A is something like the maximum force as a function of load for the 2 different solvents. Then the calculated maximum height of the potential energy surface, and then this eta parameter. So you remember that eta, if eta is smaller than 1, you would have a smooth sliding. If eta is larger than 1, you get stick slip, because essentially the height of the energy potential is larger than the elastic energy stored in one slip, in one sticking phase, essentially. And then essentially his result is higher friction in borate buffer is because there's a stronger propensity for double slips. That is his conclusion. So let me put up images, icons for the 3 topics, and I'm happy to answer any questions and enter discussion on this.
Okay, questions? There's one over here.
Thank you very much. I have a question about the beginning of your talk. You said that when you exert the pressure on the graphene, you observe that it goes to the diamond state. So I want to ask, have you ever observed, or do you ever expect, by exerting a pressure, you dimerize graphene, and you change it to the insulator state instead of making it diamond?
We are working hard on this. So we do measure the electric conductivity in normal direction with the tip, and we have seen it and we have seen it not. The problem is that electrical conductivity in AFM is dominated by the Schottky barrier, which is formed by doped silicon oxide, graphene. And how this Schottky will change when you actually enter this regime is completely unclear to me, in particular when at the same time you induce plasticity in the silicon oxide. So we have repeated this with doped diamond tips. But we feel that the doped diamond tips always have some graphitic layer at the end. So it's not really less complicated. But the main answer is probably stay tuned. We don't know yet.
Okay, thank you.
Elisa has claimed that she has seen it in the paper, but we are not so systematic about it. But we would love to say yes, of course.
Okay, over here, Lars.
I have so many questions, Roland.
You get one.
Nice talk.
So the rest are at the coffee.
So with respect to the one comment and one question with respect to two graphene layers. Isn't what you're seeing essentially what Elisa and Angelos have in their paper? That you get, I mean, if you have two graphite layers and you weld them together, you have something like a tiny piece of diamond, right? You can,
yes,
from a diamond 111, you can remove a piece of graphite.
We were originally thinking that forming these layers was giving dissipation.
Okay.
That's not the case. Breaking the
Okay.
covalent bonds as well. And what they calculated would never work in our case because we have a passivated silicon oxide layer, and with that one, the DFT calculation, we don't see it anymore. That DFT doesn't work for us because you need the reactive confining surfaces to create the minimum in the diamine. And if you don't, like us, then there's actually no local minimum.
Okay. Also, the same thing on slide 14, you had this curve where you had to jump at 12, 13 gigapascal. So this was a calculation, right, that had no silicon in it, I guess? Or was it this one, the left one? The next slide. Yeah.
This one?
Yes, this one. Yeah.
On the left is the calculation, yeah.
Okay, so because, I mean, silicon has a phase transition at that pressure from silicon 1 to silicon 2, from diamond cubic to beta tin. So if that pressure is really relevant, can you be sure that your that your silicon tip is not transforming into beta tin during the experiment?
Pretty much. Let's say, I don't think that the pressure is that high in the silicon. It's only that high in the local apex of the silicon oxide. And we do have plastic deformation of the silicon oxide, absolutely. And we can even show you the number of silicon bonds that all of a sudden pop up. So actually the average configuration of the silicon oxide changes at this point. But it's really not such.
Okay, I think we have time for one last question before we go to our coffee break.
Could you have bring next slide? In this structure, did you have any possibly increasing in temperature and so on due to creating and breaking this covalent bond between the two layers, possibly?
In the simulation,
in experiment,
there's a control temperature. And we have done the same simulations at higher temperatures, and actually the whole thing happens a little earlier, but the qualitative is the same. And in AFM, I don't believe there's a big increase in temperature because it's just such a well-conducting system, and it's only this tiny nanometers. So within reasonable timescales, it's probably...
Since creating this sp3 bond between two layers decrease thermal conductivity of graphene, and it may just increase in it. I would wondering, is there anything on that?
I don't know. Has anyone calculated the phonon spectrum for this system already? Everybody says no.
Thank you.
Okay. All right. Let's thank Roland and all of the speakers for this afternoon session. We are running 10 minutes behind, and the discussion's important, so we will start 10 minutes later, so we will reconvene at 16:50. See you then. I have a question.